up through chapter 5. Let me just show you for the homework. We're going to have a little bit more today, and we'll have Monday when we come back when we'll review everything, because it's going to be 3, 4, and 5. But you already know a few things that are definitely going to be in there. You will definitely have a multi-loop circuit, and then your part of that will be a yeah, it is for your response, but it will be, you'll have some extra credit attached to that too. So if you want to learn how to do that, it'll be worth, let's say 5 points. That's kind of a lot, but a lot of your doesn't, so maybe it's worth 5 points. So where you solve the system of equations by using the matrix, inverted matrix, do the identity matrix. So you'll have that. The equations will be pretty simple. I'll make an easy to solve system of equations, but I'll be looking at you set up the equations correctly. You'll have a cross product, the force on a charged particle moving in a magnetic field. You'll also have a combination circuit of resistors, kind of like we've worked in class where you have a bunch of resistors, 5, 6, 7 resistors that are set up in series and parallel, where you have a voltage and a current on each of the resistors. And I will have the answers come out better than I had them come out with in class. But it'll be like someone to perfect in your homework too. You'll definitely have those things. So if you want to prepare with a grade, I'll make sure that you can do those things. Do the cross product on the force, on a charge, and a magnetic field. Do a multi-loop circuit. Do a combination circuit. Yeah, and then there might be a free response about your household. I'm not sure what the others will be, but otherwise you can go the concept test over your notes, go over the homework. The homework, people often miss out on the homework. They don't really spend much time on the homework, but sometimes I pull problems directly from that homework, so I would go back and do that as well. And plus there are multi-loop circuits there for you to practice combination circuits, that sort of business. All right, let's just do a quick little cross product, get those chops moving again. There's a little bit of space on the bottom of this page. And then we'll do another one soon, but let's just say that I have 2 vectors. Let's say that my first vector, the vector A, is 3i minus 4j plus 2k. And then let's say that the vector B is 2i minus 3j. And I want to know what is the cross product A cross B. All right, just take a moment to do that cross product. What is the cross product A cross B? And remember, this will be a vector, not a scalar like we had with dot products. So it will be in vector notation. And similarly on the test, I'll just be asking for the force in vector notation. So if you know how to do a cross product, you'll be good to go. Remember, some of your terms go to 0. Anytime you're doing I cross I, that's going to go to 0. R, J cross J, that will also go to 0. I'm going to start writing some stuff down here.
should have something like this. Noticing some of these terms go away. This goes away, and this goes away. And then we'll need to determine now what are the values of I cross J cross I, K cross I, and K cross J. Use our right-hand rule for that. You know what I cross J is equal to? It's either plus or minus K. It's plus K, right? Use our right-hand rule. You can set up your, I always like to draw my coordinate system. This is I, this is J, this is K. Do this a couple different ways. I showed you last time, you let your first finger go in the direction of I, this finger go in the direction of J, and then your thumb gives the direction of K. You can do it another way if you don't like that. You can let your fingers go in the direction of I, fold towards J, and then your thumb points out and gives the direction of the resultant vector, which is K. But the end result is that this is minus 9 times plus K. And remember, with cross products, A cross B is equal to negative B cross A. So they're not commutative. In fact, if I switch the terms, I negate it. So if I do J cross I, that's going to be minus 8 times negative K. And then I have the K cross I plus 4. So what is K cross I? Finger in the direction of I, K rather. Middle finger in the direction of I. So K cross I is what? Did I do that wrong? Oh yeah, I did do it. No, it's positive J. Am I doing it? Yeah, positive J. Yeah, so index of the finger in the direction of positive K, middle finger in the direction of I, and then my thumb goes up. That's the J vector right here. So K cross I is equal to positive J, minus 6 K cross J. What is K cross J? It is negative I, right, so negative I. All right, so that gives me my final answer, which is going to be, let's see, these two combined, negative 9 plus 8. So that's going to be minus K plus 4J plus 6I. All right, so we're going to use the cross product to determine the force on a charged particle as it moves through a magnetic field. Later, after this test, and might get to it on Monday, probably not, but we'll see that this becomes relevant when we're talking about things like mass spectrometers, because well, we'll get to that. Let's just sort of work on the mechanics of doing this first. May I go down from here, y'all? Don't worry, if you don't get the right-hand rule right now, we're going to do it quite a bit to look at how these vectors, these three orthogonal vectors, are all related. Do want to just point out to you, though, that they are orthogonal. So if ever I have a vector in one direction and another vector in the other direction, the third vector has to be on the unoccupied axis. So if I have I, J, the other one has to be plus or minus K. Or if I have J, I, the other one has to be plus or minus K. That third vector always has to be orthogonal to the first two vectors. All right, so charge moving through a magnetic field experiences a force. That's equal to Q, that's a scalar quantity, times V cross B. You can multiply a scalar quantity times your cross product. So like, for example, if I had, well, we'll see. We can multiply a cross product by the scalar quantity, and then it just distributes across each term. So say, for example, I was looking at 2 times, let's say the result of V cross B was 3I plus 2J. Then this would be equal to 6I plus 2J. We've done that with vectors before. 4J, thank you. I can distribute it in that way. So it is distributive with scalar quantities. So if I multiply a vector, which is this, times a scalar quantity, I just distribute it to each term. In this case, I double each term. We've done that before, like with our F equals ma. Our m was a scalar quantity, and we can distribute that mass to all the terms of the acceleration vector. All right, the magnitude of this force just by the definition of our cross product is QVB sine theta. Remember, A cross B, general rule for cross product is equal to AB sine theta. And so that's where that comes from. And also, you can think about this in terms of this sine theta term gives us a component of one vector that's perpendicular to the second vector. So for example, if my velocity vector is in this direction and my magnetic field vector is in this direction, this is my angle theta. What that angle does is it gives me a component of one of the vectors that is perpendicular to the first vector. So now I'm multiplying V times perpendicular or the orthogonal component of B. Or you can think about it in terms of this being perpendicular to B. Either way, it's fine. But the sine theta term simply takes a component that is perpendicular to the other vector. So I'm always dealing with two vectors that are orthogonal. Remember, this is different from the dot product where we are looking for parallel components, not orthogonal components. A lot of this chapter is really just sort of dealing with the cross product more. It comes in, especially if you're an engineer and you go into higher level classes, you'll see the cross product come up again as you deal with things like fluid flow, where you have a lot of rotation going on. All right. The SI unit for the magnetic field is the Tesla. Of course, that's after that scientist, Nikola Tesla. Have y'all seen the movie about him? The Prestige. I think I've already asked y'all this. Yeah, The Prestige is about Tesla. He was actually fairly important to the development of the way we use electricity today. We'll talk about that later. In terms of, do we use AC electricity or DC electricity, direct current or alternating current? We'll talk about that later, but there was a period in our history when people wanted to use direct current, and it would have made our electrical grid quite a lot different. Mm-hmm. Yeah, they also have to have like pumping stations of sort every mile or so where they actually pump the current, whereas with AC electricity we can have these huge power lines that go across the country. Anyway, we'll talk about that later. Sometimes, we don't use this in this class, but sometimes you'll see it in Gauss. And this is our conversion factor for Tesla to Gauss. But I'm not sure if that's right. Let me double check that. Yeah, that's right. One Tesla is 10 to the 4th Gauss. Okay? We're not going to use Gauss, but you might see it elsewhere if you're doing a standardized test like, I don't know, the MCAT or whatever. All right? You will see on the next test so you'll see a couple things. And so if you look at the homework, by the way, just a quick little side note. If you look at the homework for this chapter, the homework that you should be up on are homework problem number 1, 2, 3, and 4, and also 5. Numbers 4 and 5 are both cross products. 1 through 3 are just applications of the right-hand rule, and you'll see those in the multiple choice. It might seem a little strange to you at first, but once you get the hang of it, it'll be easy, and we'll do a lot of practice. Okay, let's try these. Here I have two vectors. Just like we did with the I, J, and K vectors when I did I cross J, J cross K, all that business. Here I have two vectors, and I just want to know what is the force on these charges that have a velocity in some direction and a magnetic field in another direction. So use your right-hand rule, use your right hand, which you should always carry in your back pocket along with that positive test charge. Never leave home without it. So let your fingers go in the direction of B, or your index finger, your ring finger in the direction of B, and then your thumb gives the force. So I want to know what is the direction of the force for these three situations. Take just a second, try to figure out the force for each of those. Remembering that the force is always going to be perpendicular to the two vectors that are shown. It'll be orthogonal.
We answered it like it's a vector.
Yeah, just draw it as a vector. So for example, this first one, v is in this direction. I have to rotate around like this because b is in this direction. So my thumb points out of the page. So my force is out of the page. It's in the plus k direction. Or I would draw my force like this. That is the plus k direction. Do it for the other two. It really helps to use your hand when you're doing this. I see that not many of you are doing it because it sort of feels strange when you do it at first, but it does really help to use your hand because it's hard to orient these vectors in your mind and to think about them just in your mind. So don't be afraid to use your hand. To practice, you'll have to do it on the test next week. All right. So here, what's the direction of the force in the second one? No, it's going to be to the right. All right, so V is in this direction. My magnetic field is into the page like this. So I have to have my finger pointing into the page, and so my thumb is to the right. Another way you might want to do this, I find this a little easier. It's just that my fingers go in the direction of V, and then imagine that my magnetic field is coming out of my palm. That's the same as this, but it's just a little easier mechanically. Let my fingers go down, or you can think of it as folding towards the magnetic field, and then the force then is to the right. You know what? Another thing you can do. When I go to church with our little girl, sometimes she gets bored, and we'll like make little puppets in our hands like this, and like we'll have all different characters, like a happy face and a sad face, angry face, and an upset face and all that. And then we have like a little play there, and then my wife's like, "What are you doing?" Right? Anyway, you could do don't do this for the test, but you could do, well, my v vector is right here, and my v vector is right here, and then this is my force vector, in case you forget. Like, well, like a Sarah Palin kind of move, where you write the notes on your hand. But don't do that for the test.
Oh my God. Oh my God.
All right. But if it helps you while you're practicing, that's fine. Okay, for this last one, V is out of the page. It's like an arrow coming towards you. B is down. What's the direction of the force? Now remember, I know it has to be left or right, right? Because the B is down, V is in the Z direction, so it has to be in the X direction. Let's see, I'll take to the left. So let's see, V is out, V is down, like this. So no, it's going to be to that direction. V is out of the page, yeah. So it's going to be the same as the middle one. Don't worry, if you don't get this, we're going to have several more practice trials, and then there's some in the homework. Are you doing right hand rule, or are you erasing again? What's up? Is V or X? Okay, your velocity vector can be in any direction. So like in this case, this last one, it would be the same as doing what's V is in the K. This would be the same as doing K cross negative J. That's what we're doing, is K cross negative J, and that's equal to positive I. So here, my V, my velocity vector, is in the K direction. I mean, what does this symbol mean? Is that what you're asking? Okay. Yeah, so V is in the out of the page, V is down in the negative J direction, and so F then is to the right. Don't worry, if you don't get these three, we'll have several more to practice. Let's try these. What is the direction of the magnetic field that creates a force as shown? So here you have to work with backwards. thinking about, well, my index finger is V, my ring finger or my middle finger is B, and my thumb is force. So here you're giving other components of that. So V, force is out of the page. What is the direction of the magnetic field? And then on that third one, I want to know what is the direction of the velocity vector. All right. Let's see. V is up. My force, which is my thumb, is out of the page. That means my magnetic field is to the left. So V here is to the left. Here, V is into the page, like this. F is like that. So my magnetic field is what direction? It's down, right? And here we're working with our magnetic field vector. My force is down. See, my magnetic field vector comes out of the page like this. And so my velocity vector is to the what? Left or right? It's to the right. So here, my velocity vector is to the right. Really no easy way to figure out how these vectors are oriented except for the right-hand rule. Some of you might be able to visualize them in your head, but I never really met a student that could do that. But some of you might be able to do that. So practice that right-hand rule. We'll have some clicker questions to try it out. There's some variations of it. And we'll actually see different variations of the right-hand rule coming up after this exam, where we look at the force on a current-carrying wire, which is the principle behind electric motors and generators, and also we'll use the right-hand rule too to determine the magnetic field created by a current-carrying wire. Like with that electromagnet, when we run a current through a wire, it generates a magnetic field. Let's try this. A negative charge enters a magnetic field as shown. In what direction will it feel a force? Now let me tell you something. I haven't told you this yet, but if I have a negative charge, the force is in the opposite direction. Right, because I have this force equals QV cross B. If this is negative value, if I have a negative value, it just negates all the terms of that vector. So what was positive becomes negative, what was negative becomes positive, and it switches the direction of the vector. So when you have a negative charge, you'll figure it out using your right-hand rule, and then you just say, oh, this is a negative charge, and you flip the direction. I'll try to make it very clear if it is a negative charge. Like I did here where it's bolded and italicized. All right, about 15 more seconds. Stop at 105. 105. Not quite getting this just yet. That's okay. Sort of all over the board here. Let's see, we're going to let our index finger is V, right? That's V. My magnetic field is in what direction? Into or out of the page? This is out of the page, so that means I have to sort of resituate my hand like this, so that my ring finger, my middle finger, points out, and then my thumb points to the right. But since it is a negative charge, that means it's going to be to the left. So B is the right answer there. My index finger in this direction, my middle finger in this direction. If I do that, it gives me a force to the right, but because it's negative, I know that my force must be to the left. So B is the right answer there. C is the next best answer, but it's still wrong. You want to make sure that you switch the direction if it's a negative particle. By the way, that's going to make this particle follow a path that will look like this. And if you know, have y'all used a mass spectrometer before? Yeah, mass spectrometer is used to determine the charge to mass ratio of certain particles, and it uses this idea. You measure the radius of that path, and it will tell you what is the mass to charge ratio of a particle. We'll get into that later. All right, let's try this example. I'm just going to do this, this cross product. This would be like your test question, something very similar to this. You'll have a charged particle moving with a velocity in a magnetic field, and then I'll ask you what is the force in vector notation. If you can do this example and the next one, you probably don't need to study this. I'll give you a couple minutes. Head start. I'm going to go and expand this. You might not write all these terms because, as you know, some of the terms go to 0. First, I'm being careful to make sure I get the order of my vectors correct. So the order of the cross product is very important. Inner is plus 1 j cross I. It's 3 j cross j. Some of these terms do go away. Which terms go away? Like terms or dissimilar terms? Like terms go away because they're parallel to one another. I and I are parallel. Likewise, I cross negative I would also go to 0. But if you're parallel or anti-parallel, that cross product is 0. Because remember, the cross product takes perpendicular terms and takes a product of them. So these are both going to go to 0. So I'm left with Q times minus 6. And now I need to think, what is I cross j? You probably remember I cross j, that was equal to k, right? And if you remember that, then you know too that j cross I is negative k. So it's minus 1 times k. This is negative k, and this is k. If you forget that, which I always do, just draw your coordinates up here and think I cross j. I, j, k is out of the page. I recommend that you do that anyway, because even if you think you've remembered them correctly, you might have misremembered them. And there are only 3 combinations really. Like if you remember I cross j is k, if you want to memorize them, this is the ones you memorize, you would say I cross j is k. Let's see, is it I cross k is j or I k cross I? That's k cross I is j. And then j cross k is I. So if you want to memorize them, those are the ones. But it's a lot easier just to do the right-hand rule. You need to know the right-hand rule anyway, because you'll see some other problems like we just did. Force vectors, velocity vectors in different directions. But if you memorize these, those are the ones. ijk, kij, jki, and then of course j cross I is negative k, I cross k is negative j, k cross j is negative I. All right, so now I'm left with q times negative 7k. Now I just need to expand this. Q is, what was it, a proton, I think? So it's going to be 1.6 times 10 to the minus 19 times 7. This is negative k. So that's 7 plus 4.2. 11.2 times 10 to the minus 19. Okay, negative. And that's your answer. It's in newtons. In this problem, I asked also what is the magnitude and direction of that vector. I'm not going to ask you this on the test, but you need to know how to find the magnitude and direction of a vector. I'm pretty sure you do that by now, but you could see it on the final coming up not that long from now. If I wanted to know, well, this one's easy. Because the magnitude is just this, and the direction is in the minus k direction. But if it had an I and j term, then you'd have to do that tan theta term and all that business. But you're not going to have to do that for the test coming up. Okay? Y'all clear on that? I think you have to do it in the homework, but not for the test. I'll just ask it for you in vector notation. All right. We do another problem. So if you get this one and the next one, then I wouldn't even worry about this. You'll be fine on the test. So just try this one. Force and vector notation. Again, I'll give you a couple minute head start. Yeah,
When you have a charge opposite,
right.
if
If
you
you have,
wait till all the way at the end to do that,
I'll show you when we get to it. Yeah, you just distribute that scalar quantity. So you should have something like this. Noticing some of these terms go to 0. You don't even need to write them. Actually, it looks like just that one. And now we need to know what are j cross I, k cross I, k cross j. I, j, k. J cross I, you probably remember that. That's going to be what? Negative k. So it's going to be q times negative 12k. K cross I, j, right? Plus 18j. And k cross j, yep, negative I, minus 24I. And then we distribute that charge, which was minus 10. As Desiree said, it's going to be minus 10 distributed to all of these 3 components. So I'm going to have 120k minus 180j plus 240I. All right, it's going to be in newtons. I do want to point out, I just give you all these numbers because they're easy. I just want you to be able to use the cross product, and we'll apply it a little more later, but this is more I just want you to be able to use the cross product. Some of you could see it again. You chemists probably won't see it again, but you engineering students probably will see it. The cross product. But I also want you to realize that all these numbers aren't really realistic. That normally our charge would be a lot smaller. Right? Like the charge on an electron is like 10 to the minus 19 coulombs. So to have a 10 coulomb charge is a really big charge. And then also, our velocity going along at 2 meters per second is pretty small for a atomic particle. Usually when we're dealing with them in the lab, they're going to be going like millions of meters per second. They're going really, really fast. So that's not really realistic. And then our magnetic field, if you remember in the lab, you measured the Earth's magnetic field. It was like, micro Tesla. So this is a pretty big magnetic field. A Tesla magnetic field is something you would get in like in a lab that deals with very large magnetic fields. Alrighty, let's try some more right-hand rule stuff with the concept questions. Here in the back. You'll have some multiple choice questions like this, and those first few homework questions will help you with it too. So let's see how we're doing with this. Positive charge enters a uniform magnetic field. What is the direction of the force? All right, we'll stop at 55. 55. I'll go to 58. Okay, is that right? Yeah, that is right. The force is going to be to the left. Seems like a lot of you have it, but some of you still don't have it just yet. I let my finger in the direction of V. My magnetic field here is into the page, and so it's going to be in this direction. To the left. Remember, it has to be either to the left or right, because I have V in the Y direction, B is in the Z direction, so it has to be in the X direction, either to the left or the right. It's just, is it positive or negative X? Positive charge enters a magnetic field as shown. What is the direction of the magnetic force? Here, V is in the X direction, and B is in the Z direction. So I know my force has to be orthogonal to those.
on the Q you know, folks say like it's clear. It's supposed to be that it's.
Oh, yeah, the colors can come through. Doesn't matter.
That doesn't have anything to do with it.
The only thing with the charge is it positive or negative? And it'll say in the prompt if it's positive or negative. Or if it's negative, it will say. You should always assume it's positive unless otherwise.
All right, I'll stop at 108. 108. Okay, D is right here.
I let my index finger go in the direction of B. Magnetic field is into the page, so the force is upwards.
Let's try the next one. A little more difficult. Oh, this was not too difficult. Here's a positive charge. V is up. B is to the right. All right, folks.
First off, you should just eliminate answers that you know can't be true. Some of you have those answers. V is in the Y direction, so the answer can't be in the Y direction. B is in the X direction, so it can't be in the X direction, so it has to be in the Z direction. So it has to be either A or B. It cannot be D or E. It's not C, it's not zero. There is a force on it because the magnetic field and the V vectors are perpendicular to one another. So it has to be either A or B. All right, good. So let's think about this because you are still sort of split. I let my finger go in the direction of V. And then I take my index finger and I point it in the direction of B. And then my thumb, when I do that, my thumb of my right hand will give the direction of the magnetic force.
We try that. About half of you had the wrong answer. Okay, it's a little better now. All right. I'll stop at 142. Okay, it's a little better. B is right, into the page.
V is up, B is to the right, so my thumb is pointing into the page.
Oh, what's the direction of the magnetic field here? Y'all have it in your book?
Yeah, they're all arrows up.
Okay, yeah. So the magnetic field here is up. For some reason it got washed out.
The magnetic field here is up, B is also up. What is the direction of the magnetic force?
That would be like J cross J, right? Alrighty, I'll stop at 45. 45. Okay, good. C is right. Hey, do y'all know why a gorilla has big fingers? It's got big nostrils. Okay. Oh, I'm sorry. So here the answer is C. When they're in the same direction, my cross product goes to 0. J cross J is equal to 0. Because the cross product, remember, is perpendicular vectors, orthogonal vectors, and if they're in the same direction, there's no force at all. So if my velocity vector is moving in the same direction as the magnetic field, there are no forces acting on it. Okay, here a beam of atoms enters a magnetic field region. Which path will the atoms follow?
Let your 1 be A, 2 be B, 3 be C.
Ask your neighbor what they're putting. Y'all are sort of split on the answer. So ask your neighbor what they put. More people have the wrong answer than the right answer, so beware. All right, we'll stop at 1 minute. 1 minute. Hey, and Adam walks into a bar and he asks the bartender for a drink. The bartender gives him a drink, and Adam says, "Hey, how much?" And the bartender says, "For you, no charge." Right? And Adam doesn't have a net charge, right? If it's an ion, a cation or an anion, it will have a net charge, positive or negative, but an atom has no charge. So the answer is going to be what? B, right. Another problem with this is that if it was a positive charge, which is what y'all thought, if it was following path number 1, you were thinking, it has a positive charge that follows this path. That's a problem because it turns out that the electric force, or excuse me, the magnetic force is a centripetal force, and we'll see this next time. And that's why we use it. That's why mass spectrometer works, which we'll get into after the break, after the exam. And a centripetal force is always going to cause what type of motion? A curve, right, a circular path. And so if it was a positive particle, it wouldn't follow path 1 because this is not a curved path. It would follow a path that looks like that. The force that causes motion, like in path 1, is a force that acts at this point and this point alone. And then that force goes away, and the particle continues in a straight line. So there are no forces acting on a particle traveling through path number 1. So B is the right answer. Path number 3 would be a negatively charged particle. 1 and 4, they can't happen. All right, listen, we'll come back to these, and we'll finish these up on Monday. And then I expect us to do some review. So look over it over the break, and bring any questions that you might have on Monday after the break. But listen, y'all have a good break. Be safe. Be stupid, okay?